In this video, we're going to start our discussion of infinite series. Let's start with infinite sequences. This is what we discussed in the last module. We have n goes from 1 to infinity, and we have these sequence of terms that are separated by commas, a1, comma, a2, comma, a3, all the way to an, and so on and so forth. With an infinite series, the difference is we have a summation. Summation n goes from 1 to infinity. So we have a1 plus a2 plus a3 all the way to plus an and so on. So the key difference between a sequence and a series is that a sequence are terms separated by a comma, whereas a series are terms that are added up and are separated by pluses, and that's why we have a summation for an infinite series. We can define an infinite series as a sequence of partial sums. Summation ak, k goes from 1 to infinity, is a1 plus a2 plus a3 plus ak plus 1 and so on. So this is an infinite series. Let's look at a sequence of partial sums. S1 equals a1, that's just the first term. S2 is the sum of the first two terms, a1 plus a2. S3 is the sum of the first three terms, a1 plus a2 plus a3. And Sn, the nth partial sum, is the sum of the first n terms. Sn is equal to a1 plus a2 plus a3 all the way to an. Now let's consider the sequence of partial sums, S1, S2, S3, comma, and all the way to Sn. If this sequence, Sn, converges to S, then we say the series, summation k goes from 1 to infinity ak, converges to S. So this is the connection of sequence and series. We say a series, an infinite series, converges to S if the sequence of partial sums converges to S. Alright, so we've defined S to be equal to k goes from 1 to infinity, ak, where S is a sum of the series. If the sequence of partial sums, S1, S2, S3, all the way to Sn, or just writing it as Sn, diverges, then the series k goes from 1 to infinity ak also diverges. That means there is no sum. So let's do a summary. If the sequence Sn converges, that's the sequence of partial sums, then the limit as n goes to infinity of Sn is equal to S exists. Then the series k goes from 1 to infinity ak converges, and the summation k goes from 1 to infinity ak, this infinite series, which is equal to a1 plus a2 plus a3 plus an and so on, is equal to S. It has a finite sum. The infinite series converges to a finite sum. S is a sum of the series. Otherwise, if the limit of the partial sum Sn as n goes to infinity does not exist, then summation k goes from 1 to infinity ak, which is this infinite series, is said to diverge. Summation k goes from 1 to infinity ak is equal to limit as n goes to infinity of the partial sum k goes from 1 to n ak is equal to limit n goes to infinity of Sn is equal to S. This series converges to the sum S. Alright, let's look at an example. So here we have, does the series summation k goes from 1 to infinity ak converge or diverge? So let's consider the nth partial sum. Sn is equal to k, where k goes from 1 to n. This is equal to 1 plus 2 plus 3 all the way to n. Now let's look at the sequence of partial sums. Sn, n goes from 1 to infinity. This is equal to S1, S2, S3, all the way to Sn, and so on. Alright, so let's look at the first term. S1, the sequence, the first partial sum is just the first term. S2 is a sum of the first two terms, is 1 plus 2 is equal to 3. S3 is a sum of the first three terms, the third partial sum, 1 plus 2 plus 3, and that's equal to 5. And in general, the nth partial sum, Sn, is 1 plus 2 plus 3 all the way to n. But you might recall from earlier on when we were looking at Riemann sums, we actually have a closed formula for Sn. Sn is equal to 1 plus 2 plus 3, the sum of all these integers from 1 to n. We have a closed formula. This is equal to n times n plus 1 divided by 2. That means summation k goes from 1 to infinity, is equal to limit n goes to infinity, k goes from 1 to n, k, that's the term ak, I suppose. This is equal to limit n goes to infinity of this summation, this nth partial sum. We have a closed form for it, which is n times n plus 1 divided by 2. So n times n plus 1 divided by 2. And this, of course, is infinity, because we get n squared limit n goes to infinity of n squared plus n divided by 2. And if we take the limit of this, the numerator grows large and just progresses on to infinity, and denominator is just 2, so this ratio approaches infinity. That means this series, k goes from 1 to infinity, k diverges to infinity. So it does not converge. This series diverges to infinity. All right, let's look at another question. Here we have proof that the series k equals 1 to infinity 1/3 to the k converges, and find its sum s. So let's start by expanding this series. We have k goes from 1 to infinity 1/3 to the k. This is equal to 1/3 plus 1/3 squared is 1/9 plus 1 over 27 plus 1 over 81 plus all the way to 1 over 3 to the k. That's the kth term. And it's an infinite series, so we put dot, dot, dot. It goes on forever. So let's consider the nth partial sum, which is Sn, is equal to k goes from 1 to n 1/3 to the k. So we have S1, that's the first term, is 1/3. That's the first partial sum. S2 is the sum of the first two terms, 1/3 plus 1 over 9. So 1/3 plus 1 over 9. This is equal to 4 over 9. And S3, the third partial sum, is the sum of the first three terms, 1/3 plus 1 over 9 plus 1 over 27. 1/3 plus 1 over 9. Taking common denominator and adding these fractions, we're going to get 13 divided by 27. And similarly, S4, the sum of the first four terms, which is 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 81. I shouldn't really have a dot, 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 dot here. I should just have 1 over 81 and then plus all these dots. Let me make that correction here. All right. So S4 comes out to be 40 divided by 81. If we add the first four terms, which is 1/3 plus 1 over 9 plus 1 over 27 plus 1 over 81. And of course, this goes on, and we can find the partial sum for any index k. So the pattern for the nth partial sum seems to be Sn is equal to, well, in the denominator, that's fairly easy. We just have 3 to the n, because we have 9 here, which is like 3 squared, 27, which is 3 cubed, 81, 3 to the 4th. The numerator is a little bit harder. So if we take 3 to the n minus 1 divided by 2, that should give us a numerator. For example, S3 is equal to 3 cubed minus 1 divided by 2 times 3 cubed. So let's try that. 3 cubed is 27, minus 1 is 26, divided by 2 is 13, divided by 27. We can verify if this formula is true by using mathematical induction. So let's write that. Let's use mathematical induction to prove this formula is true for all n. That's what we need to prove. We have shown that it holds. This formula is true for n equals 3. So we're now going to assume that the formula is valid for n. So Sn is equal to 1/2 times 3 to the n minus 1 divided by 3 to the n. Now Sn plus 1 is the nth partial sum plus the next term, which is an plus 1. This is equal to 3 to the n minus 1 divided by 2 times 3 to the n plus the next term, which is 1 over 3 to the n plus 1. We take common denominator, which is going to be 2 times 3 to the n plus 1, and we get 3 times 3 to the n minus 1, taking common denominator, and plus. So 3 to the n plus 1 goes into 2 times 3 to the n plus 1 2 times, that's plus 2. If we simplify this, we get Sn plus 1 is equal to 3 to the n plus 1 minus 1 divided by 2 times 3 to the n plus 1. So by induction, the formula for Sn holds for, or is true for, n plus 1. Holds for Sn plus 1. And hence is true for all n larger or equal to 1. That means the sum of the given series S is equal to limit as n goes to infinity of Sn. This is equal to limit as n goes to infinity of k goes from 1 to n of 1/3 to the power of k is equal to limit as n goes to infinity of 3 to the n minus 1 divided by 2 times 3 to the n. Now let's split up the fractions and take the limit. So we have S is equal to limit as n goes to infinity 3 to the n divided by 2 times 3 to the n minus 1 divided by 2 times 3 to the n. Now the 3 to the n cancels out, and we're going to get limit n goes to infinity of 1/2 minus 1 divided by 2 times 3 to the n, and this is just going to be equal to 1/2 because this term 1 divided by 2 times 3 to the n approaches 0 because 3 to the n, the exponential function in the denominator, grows to infinity as n goes to infinity, so the result is just 1/2. So what we have shown is that the summation k goes from 1 to infinity 1/3 to the k converges, this infinite series converges to the sum S is equal to 1/2. So summation k goes from 1 to infinity, let's expand the series 1/3 to the k. This is equal to 1/3 plus 1 over 9 plus 1 over 27 plus 1 over 81 all the way to 1 over 3 to the k plus dot dot dot. This is an infinite series. this sum converges to 1/2. It has a finite sum. This infinite series converges. So this infinite series converges to the sum S is equal to 1/2. All right, thanks.